Welcome, Morgan.
Thanks, Kirsten. I can't think of any better way to spend my day teaching you about fusion and fission. I brought my assistant, Michelle, to help me display the processes of fission and fusion.
Welcome, Michelle. Now let's get this show on the road.
If you'll follow me to the supersonic slippery slide, we'll take you to the sun. Now, the supersonic slippery slide is no normal means of transport. Since the sun's UV rays are very harmful for your eyes, be sure to secure your sunglasses tightly. Also, keep all arms and legs inside the vehicle at all times. Everybody ready?
Yeah!
Here we go! We're here in the sun's core. Woo, it's hot in here.
Nah, that's just me.
Okay, well, anyway, now that we're here, we're going to demonstrate the process of fusion in the sun's core. Amy and Michelle are here to show us.
Okay, so I'm an expert on fusion, and we are in the sun's core, and for this demonstration, I'm going to be a nuclei.
And I'm a nuclei.
And we're going to start jumping to create energy to eventually be bonded together. So we start off jumping slow, just to build up energy.
And this is a slow motion demonstration.
And then eventually we pick up more speed.
And fuse together into one new atom.
Now that we showed you a slow motion reaction, we're going to speed up the reaction and show you a real life example. Now that we've traveled from the sun's core through the supersonic slippery slide, we're going to explain fusion in a little bit more detail. First, fusion is two atomic nuclei being forced together under high pressure. Then, the combined masses is less than the sum of the original nuclei that we started with. Lastly, the extra mass is then converted into energy using the equation E equals mc squared.
Now I'm here with Amy and Morgan to show us how using everyday objects can produce fusion.
Thanks, Kirsten. Now, don't get this confused with the real fusion reaction. This is just to help you understand the process better.
Okay, so now we're going to take you inside the kitchen and show you our nuclear fusion example. First of all, we're going to start with a jar of peanut butter, which represents one nucleus.
Then we're going to start with some chocolate. We're going to add that in, and this represents another nucleus.
And we're going to mix them together and fuse them. Fusion is two or more nuclei being fused together to form a new nucleus.
The reaction has to happen at a certain temperature, which is usually around 40 million Kelvin.
And now, we're not in a nuclear reactor, so the temperature obviously is not as high as it was before, but it will work for this example we're going to show you.
The reactions are capable of releasing large amounts of energy, and that comes from the heat released
and the pressure being forced down. And now our mixture is about to be done.
The nuclei have to overcome electrostatic repulsion, and they get close enough together for the force to become strong enough for them to fuse together.
And our mixture is just finished fusing together, and now we have peanut butter and chocolate as one new nucleus. And the overall weight of both of these is heavier than it was to start with.
That happens from the two nucleuses fusing together make a heavier nuclei.
Wow, that looks yummy and it was a good example. I learned a lot.
Nuclear fusion can be educational and scrumptious.
Now, nuclear fusion takes place in the sun's core, but it can also be synthetically made in a nuclear power plant.
Wow, I didn't know that. Though I did learn a lot about fusion today.
Like what?
I knew that there are two nuclei separate and they fuse together by high power, pressure, and energy, right?
Yeah.
Yeah, and then it forms a heavier mass, and that creates energy.
That's basically what it is. So that's all the time we have for our example. We hope you learned a lot, and see you next time.
Thanks, Amy.
Nuclear fusion is all around us, including in the stars. The pressures are enormous, and the temperatures can be greater than 15 million Kelvin. These are the kind of conditions you need for nuclear fusion to take place. Once these conditions are reached in the core of a star, nuclear fusion converts hydrogen atoms into helium atoms through a multi-stage process. To complete this process, Two hydrogen atoms are merged together into a deuterium atom. Two of the helium-3 nuclei can be merged together to form a helium-4 atom. This whole reaction is exothermic, and so it releases a tremendous amount of energy in the form of gamma rays. These gamma rays must make the long, slow journey through the star, being absorbed and then re-emitted from atom to atom. This brings down the energy of the gamma rays to the visible spectrum that we see streaming off the surface of stars. Stars can emit energy as long as they have hydrogen fuel in their core. Once this hydrogen runs out, the fusion reactions shut down and the star begins to shrink and cool. Some stars will just turn into white dwarfs, while more massive stars will be able to continue the fusion process using helium and even heavier atoms.
Now that we've shown you fusion, we're going to show you fission as well.
Since Amy is the expert on fusion, I'm the expert on fission. Fission occurs when only between uranium-235 or plutonium-239. And this happens when a neutron goes at a fast rate and hits the nucleus of either uranium or plutonium. When it hits the nucleus, 3 separate neutrons or more bounce out of the nucleus, along with 2 new fission products, which would be 2 new atoms. But the mass of these 2 atoms is less than the mass of this original nucleus, which means that the extra mass is converted into energy through E = mc². These other neutrons can bounce off and hit other nuclei, which creates a chain of fission reactions. These reactions create so much energy that 1 kilogram of uranium-235 equals 200,000 tons of dynamite. These reactions take only fractions of a second and are used in atomic bombs and create power and nuclear power. This is a slow motion demonstration of fission. We are the nucleus of either uranium or plutonium. Okay, so I remain here as part of the mass of the original nucleus. Kirsten here is part of the mass of a new nucleus, or of a new atom, and Amy is part of another new atom. Now also, there would be 3 or more neutrons bouncing around along the outside. When Amy first ran in, she was a nuclei coming at full speed to break us apart. Now that we have these 2 new atoms, they are slightly less than the mass of when Kirsten and I were together. This extra mass that is not used is turned into energy through E = mc. Here's an example of a fission reaction in real time. And I'm the extra energy jumping around while these 2 are the new atoms.
Hi, we're here outside the experiment station. Michelle, what are you going to show us today?
Well, today we're going to do a real-life example of fission. Now, this isn't actually what fission is, but it will help using household objects to show you kind of what the concept of fission is. We have here an egg and a knife. So you know this experiment's going to be interesting. Let's head over to the experiment station, Kirsten.
Okay. I'm excited for this to happen.
I'm excited too. You know, fission is an exciting process because we get all kinds of new stuff from it and we get to see stuff exploding, and it's really cool to see it in real life examples.
Yeah.
Are we to the experiment station, Kirsten?
We're about right here. It's good.
All right. Here at the experiment station. Now, what do you think an egg and a knife is going to do for fission, Kirsten?
I think the knife is probably going to poke the egg and split it apart. Just like,
Whoa!
like neutrons would into a nucleus.
How'd you guess? You must have learned a lot about fission from our other example.
I did.
So, what does this egg represent now?
I'm pretty sure it's a nucleus.
Yes, it is. This egg is the nucleus inside of, we'll pretend that there's an atom around it. Now, we have the neutron here that's going to travel at a fast speed to break into the nucleus, and we'll see what happens from there.
We're going to slow down the neutron, though, so it doesn't hurt Michelle.
I'm not holding it.
And now that represents how the nucleus splits apart into 2 different examples.
Thank you for helping me out with that, Kirsten.
It was fun.
Now, let's see here what this example really means. The yolk here is actually what the original nucleus was. And then we have these two, which are the new atoms. All of these pieces around here represent other neutrons that can go off and hit onto other nucleuses and keep creating more of these new atoms.
That's pretty interesting.
Now, you may wonder, well, these two new atoms are not quite the same mass as the original egg.
They're
right?
not?
No, because we have these pieces over here that were part of the egg, so now we have those two masses that are smaller.
That makes sense.
So what do you think happened with that mass that was there?
I don't know, is it just left over?
No, everything is useful, Kirsten. That extra mass that's not there anymore, according to Einstein's E=mc² equation, it turns into energy.
Energy?
Yeah, and that's how we get our energy in the sun. So, Kirsten, I hope you learned a lot about science today, and hopefully fission.
I sure did. I know that when the neutron goes at a fast speed and hits the nucleus, two new atoms are formed, and then other neutrons form around it, and they can go off and create more fission processes as well. Plus, the leftover mass, because when it splits apart, the masses are different, the leftover mass is transformed into energy using E=mc².
When Einstein figured out that those two new atoms were not equal to the mass of the first atom, he used E=mc² and found out that we can get energy from fusion.
That's so exciting. I'm so glad he learned that.
I know. Chemistry is really an exciting thing, Kirsten. There's chemistry in these trees, chemistry in the air around us, chemistry in our bodies everywhere.
Really? I thought it was just a periodic table.
I know. I always thought that too. But you know what? There's a lot to chemistry, and it is really cool.
Now, Michelle, let's head back to the studio to finish up our segment.
All right. I hope you guys learned everything you could about fission and fusion today.
I know. Thanks for coming in today, Morgan. I sure learned a lot about fission and fusion.
Thanks for inviting me. I hope you guys learned a lot too.
Tune in next time to learn about organic chemistry.
Odin.